Everyone, welcome back to AtCoder. And today we have regular contest. I have no idea about what is the difficulty level of these problems. If, however, the score corresponds, if the problems with the same score are the same difficulty between different contests, then I would aim for us for today to solve first 4 problems. Because last time we solved everything but 600 problem, but it was not because it was like difficult, it was because we ran out of time and also didn't think for too long. So let's see how it goes. I hope we solve around 4 problems and let's go. Okay. To be honest, I don't know how to solve this problem straight away. Suppose there is some kind of pattern to it. Because I have 10 to the huge power. Yeah, let me. Suppose that we know something as following. We have 10 to the nth, it's equal a times m squared plus b times m plus c, right? Then what do we get when divide by m and round down? It looks like we get a times m squared plus b, and c gets discarded because we divide and round down. And when we divide, let me bring all of this a bit higher. And when we let this number be k, right? And we take what is a remainder when we take k mod m? Well, it's b, right? Here, of course, we don't have m. So basically, what I think this problem is we would like a fast modular exponentiation modulo m squared. And then we would like to find this coefficient. Yeah, I think this is it for this problem. So only I would like to convert everything to int64, not to think about anything. Actually, right? Base can be huge. Also modulo. Also have power and modulo. And then it's just regular binary exponentiation. Let me see. We have result, it's initialized to 1. while we have power. If power is odd, then result gets multiplied by base, modded by modulo. Base is always multiplied by base, so that we iterate over base squared, base to the fourth, etc. And then we divide power by 2 and then return results. I think this is it. Like, this is modular power. So our base is equal to 10, our power is n, and we have modulo m times n, right? And k is what? K is like power actually does not include this part, am squared. So we just have to, or actually we are left with bm plus c, and we can just divide it by m, right? So I think we can output something as follows. Is it correct? Yes, it is correct. Okay. Yeah, apparently it sounds very reasonable to me. Let's try to submit. Okay, I was correct. Let's check the second task. Have n cards numbered from 1 to n. Each side of card has color. Okay. AI, BI, okay. Different colors showing up. Interesting. Okay, let's look at the example. So we want to select one from each pair. So the total number of different selected integers is as high as possible. In this case, I believe we can reach like 1, 3, 4, 2. Okay. Okay. Yeah, we can immediately. I don't know, let's just write some inputs. Or actually, no. And I would like to use my templates, but it's okay if we don't use them and we write a faster code as a result. And colors can be bigger than n. Okay. I mean, it's a bipartite graph, right? We can treat colors as vertex IDs. And we can also add always an edge between. Oh, wait. Is it maximum match? I need to refresh my knowledge of theory. But like anything that I know works in too long. Okay, so we want like choose one number from each pair, maximize number of distinct numbers that we picked. I don't think that greedy or anything like that will work here. It does not seem like a natural problem for greedy. What we can get here? 5, 6, 1, 7, I don't know, 2. Okay, there's 5. There's 2. Okay, so if we ever have a card with equal sides, then we can just pick it and don't pick this side in all other numbers, right? Should be correct. Also, I have concerns like about, yeah, if in any pair, if we already picked 1 anywhere, right? Then in every pair with 1, we can pick the opposite number, right? Actually, yeah, inside of connected component, like it feels like we can like take first pair, pick first, check whatever we get as a result, and pick second and check whatever we get as a result. It should be fine. Or is it? I don't know. Yeah, let me get back to our graph idea. But formulated a little bit different. So we have bipartite graph. On one side we have vertices of A. Second we have B. We have several curves connecting them. Like so, and now. I'm gonna say like in every edge, once we select like this vertex and this edge, and we can like here we select this, and because this is no longer interesting vertex. Oh, okay. So it is possible that we don't get like everything selected. despite these three being connected. Okay. Actually, what types of things we can have here? What connected components can we have? Now, one option is obviously something like this. Second option is something like this. Here we can select all four of them. Here we can select all but one. We can choose which one not to select. But it's still complicated, like not if we have several such things with different numbers. Oh, okay. What if we ignore the fact that it's B per T, right? And just like create a general graph. Let's see this example. We have, I guess, 1, 2, 4, I can see 5, 6, 7, 8, 9. We have edges like 4. We have 5, 2, 5, 6, 1, 2, 9, 7. Okay. 2, 7, 5, 5. Actually, okay. 4, 2, 6, 7. 2, 2, 7, 8. 9, 7 again. Okay. And 1, 8. Okay. Okay, so we have this connected component as such. And and what I think we can do is suppose we have like one vertex that's a leaf, right? So it has only one edge on which it can be selected. Then we select it here. Then we remove this part from the graph, and we remain with still connected graph, right? Because we removed a leaf. And once we did it, once the graph is connected, we can take any vertex that does not break connectivity. Let's say 6, remove it with this edge. And we don't necessarily like remove this edge, right? So it stays sort of. And then 5 becomes a leaf. But we can take it like so, right? And one of the vertices adjacent to it does not become like that. We can take it out with this edge, if this was not a leaf. Yeah, okay, so what I currently think is if a connected component is not a tree, then we can take all vertices from it. If it's a tree, then we can take all vertices but one. Seems very reasonable to me. Let's try to implement something like this. We'll need connected components. We'll need a graph. I have to think what happens when like we have a double edge. I think double edge means that we can still like take every vertex out of the graph. Okay, so if okay. Yeah, I think we're good. But I have like doubts about how to implement it. So suppose I have a graph. I don't really know how many vertices we need. So let's take as many as we can take. And you know, like being very precise is not always good, so let's take a bit more. Also, numbers are from 1 to 4,000, so we don't have to worry about subtracting 1 or anything. Yeah, I don't currently understand how do we distinguish a case when we have a double edge. That's all I can say. Yeah, but okay, let's write our DFS for connected components, I guess. Want graph, current vertex. I also want reference to visited or whatever. And we will also output result as we go. Okay. So I believe they usually use. Yeah, I think so. We have something like this. When we enter a vertex, we visit it, and we add it to the current connected component. Then we loop over adjacent vertices. If adjacent is not visited, also we have to mark current vertex as visited. Yeah, so in this case, I want to make another DFS. I think this is it for DFS. Now we have components. Hmm. First, we would like to create our components. Let's grab ourselves a number of vertices in the graph. Also, I believe we would like to have a vector visited. If not visited at current vertex, then we create a new component and run DFS from graph components visited and vertex. I think like so. And then I can return components. I'm really not sure what to do with like same edge going twice, one way and another. Something seems wrong. I mean, we can already get our components. No, I must be getting this problem very wrong. Let's check the next one, because I don't know, something is wrong about this idea, but I don't know what. Have n people from 1 to n and n pieces of baggage. Okay. Person I has weight and baggage j has weight. Okay. Person I has baggage pi. Okay. So we have a permutation basically. Okay. Do the operation below 0 more times. Okay. Okay. How many swaps or what? With a weight greater than or equal to his or her own weight. Oh, okay. Yeah, so here we have like these are A high, right? 3, 4, 8, 6. Here we have like 5, 3, 1, 3, and permutation is 3, 4, 2, 1. So this person originally takes this. Okay. Yeah, let me see. Like this originally has this. This originally has this. This has this. And this has 5. Okay. And they also want operations. Okay. I mean, okay. Kind of difficult. So you would like this person to get this baggage, which is original. Oh, to get this, which is originally here. Okay, what if you take like minimum person If we can't swap it, then we can't swap it, right? I mean, we would like to give this person their baggage, which is originally like somewhere else. If it's not tired, then we can give them their baggage. And this person won't become tired because their weight is greater. So if this person was not tired from this baggage, and this person won't be tired and either. And this person may get tired, but we are not interested in it anymore. And also, we obviously need. Oh, wait, do we need? I'm trying to understand whether it's optimal or not. I mean, what if we have permutation like 2, 1, 3, 4? Oh, then they are not connected. And okay, it seems optimal to me. Like in again, we have several parts that are permitted within themselves. We are not interested in anything else. Okay. I think we'll need inverse permutation. I think we will need it. First, we'll need to reach A. Actually, that was unnecessary. Okay, so first we would like to decrement pi by 1 to represent its permutation of indices. Then we would like to inverse permutation of I gets pi. Oh, that's wrong. Like we want this. Right? Yeah, that's correct. Then we would like to sort people in increasing weights. I believe that we want to keep their indices. So A indexed, again of size m. Yeah, so as it explains. Parallels somewhere in the total. So when we sort A indexed, we'll have correct order of people, and we'll also know like who do we want to swap with. Okay. Operations, let's call it like so. Also, let's create boolean flag possible, which is initially set to true. If possible, then we want to output. What do we have to output if nothing is possible? -1, okay. Currently to-do list here. We'll first output the number of operations it took us. And then we output pairs of our permutations. The only difference that we want to output we want to output them like so. So with +1 because we decreased by 1 here. Okay. J should get AI at I second. The J is AI at I. Okay, now we want to process these guys. We have a current index in array. So if array, if the recurrent baggage is greater than AJ, and it's not possible. And we can also add it here. Else, their baggage is okay. Right? No, greater than or equal. Okay. Otherwise, the baggage is smaller and they want to get. We have inverse permutation that says like, where is my baggage? My baggage is here. Now we want to swap. Now we want to swap these guys. Okay. Also, if d at k greater than or equal to a at k, then also possible is equal to false. Else we can swap them because none of them is tired currently, right? So what does it mean to swap two of them? I believe inverse permutation of. We are interested in updating inverse permutation of J, inverse permutation of K. No? And inverse permutation of K. Because like person K, which we will swap. Wait. So person K currently holds someone's baggage, right? I need to get back to John. So I have person I, which is equal to 0. Inverse permutation is as follows. Who has baggage 1? Person number 4. Who has baggage 2? Person number 3. Who has baggage 3? Person number 1. Okay. This is inverse permutation. And J, we child here. So J is here. 3. Right? What happens when we swap them? So first, I think we can just swap b at j, b at k. Yeah, actually this strong like I means yes, okay. J and K. J and K are correct names. J and K. We want to swap their bags. We can do it because they are both smaller than their current weights. I think I actually have, okay. I'm going to make it a bit more universal. So we swap their bags and we want to update permutation. I think that we want to simply swap B at J and B at K. But what do we want to do with inverse permutation? Who has baggage J after we did? Person number J, right? What else baggage was involved? Also, B at J was involved. And now person K has baggage BJ. I think so. And also, we only need to do this if P of J not equals J. Because if it already equals, then we like already solve the problem. We can ignore it. And I think that we also want to replace back a swap of J and K. At least I think so. Let's check. When it sounds very reasonable. Okay, yes, I agree. I did not include algo. No, it's not good. It's not good. Okay. Okay. I want more information. Okay. What if we print like everything that we're interested in? What's wrong? Well, Do I not need it or what? Hmm. Where did B0 equals 5 ever came from? Ah, okay, okay. Oh, but because we are not interested in BJ, right? We're interested in B at P, okay. Because it's what this person currently holds, right? Okay, so at the beginning we have person 0. We take it because it has the lowest weight and it holds baggage of weight 1. This is correct. Its current permutation index is 2 and inverse permutation is 3, which is correct because this is 1. Okay. And K gets 3. Okay, because inverse permutation 0. A3 is currently 6. It holds baggage 5. It P3. Okay, it yes, it's correct. And its inverse permutation is 1. Okay. Yeah, because this is okay. So we add a swap. Then we consider person with j equals 1. So this one, it holds, it has weight 4. It's correct. It holds B0. Why B0? Oh, okay. B3 equals 5. It holds like less baggage. Yeah, but no, it holds like this baggage. Yeah, we have to swap not these guys, but these two, right? Again, okay. Um, hmm. I have a little bit too many permutations, don't you think so? Actually, do we want to permute baggages? I don't think so. I guess we only want to permute these two. Oh my, why is it so difficult? It should not be that difficult. Oh. Take 0 and 3, because 3 is here. We swap them. Okay. Take 1 and 2. Because this has baggage of this person. We swap them. Okay. No, let me do what. Know what? I want to permute baggages because I don't understand. Like this does not feel natural. I want to hold. No, it should be fine. I don't understand. We swap entries, pj and pk, in our permutation. Right? We in place permutation jk. So here we do permutation like 0, 3, 1, 2, 3, 1, and 2, 0, and something breaks. I don't understand what breaks. Like we can get impossible only. Why do we actually came back all the way to? Yeah, what if I print like everything before every operation? For whatever we do, let's print like everything. Also like to do like so. Okay, so initially we have 3, 4, 8, 6, which is correct. First person holds baggage 2, which is 1, correct. And 3, 1, 0. Okay, this permutation is correct. Permutation of baggages is correct as well. First permutation 3003 to 112, 0220, 1331. Okay. Then we swap. Let's see how we swap. We from here we can first we swap 0 and 3, right? And the same goes for baggages. So baggages updated correctly. Inverse permutation updated incorrectly. Okay, so inverse permutation is currently updating incorrectly. Because we should update it before we update this. Okay. 2 should be impossible, as long as I remember, and 3 should be in 0 operations. Okay, this is a correct number. I just, okay. So now we obviously don't want to print this. Yeah, let's check again. Here we should get separations that are more or less what's expected. I mean, they said that every correct solution will be accepted, so let's try this one. I'm not 100% sure, but it seems reasonable to me. Okay. So this was, I believe we're just missing something about problem B, but sometimes switching to the next problem is a good idea. Maybe to refresh your thoughts. I don't want to look at standards. I believe we're doing very poorly so far. Orientation. Have an okay, again, graph problem, okay. Undirected, well, probably more, maybe this is not a graph problem and I'm missing something. Let's see. Given undirected graph with m vertices, n edges, n vertices and m edges, just from 1 to n edges, okay. Sequence of labels, okay. Under hello. Oh, okay. So initially edges are undirected. We want to orient every edge. You want to exactly see I vertex reachable from vertex I, including vertex I itself. Okay, so obviously, or wait, we can have something like a loop, a cycle. It's okay. Output from it is very strange, but whatever. I actually don't know anything about graph orientation. I believe there are some algorithms. Let me check. I believe it's okay to like search for this theory, right? But usually they like use they have different objectives, not like make CI vertices visible. Okay. I don't think we'll be solving this. I think it's reasonable to come back to B. Have M cards. Okay. Want to pick one side for every card. Yes, so the problem was that we were not sure how to distinguish whether oh, wait. Am I stupid? I mean, whether a component is tree or not, it will just count number of vertices, right? So initial answer is 0. At the very end, we'll output it. We can loop through components. We can also make components cons, just in case. Component in components. Can get the number of vertices here. We also can make it constant to not so that we don't change it by accident later. We can then loop through all vertices in component. Edge count at 0. 3 equals edge count equals vertex count plus 1. If 3 answer plus equals vertex count minus 1, else answer plus equals vertex count. Here we want to edge count plus equals graph at vertex size. I believe we can simply check like this, whether a component is a... We are supposed to get 4. We're clearly getting too much. Interesting. How would that happen though? I mean, yes, we have component that is like, but we should get like vertex count equals, I don't know, edge count for this extra component should remain 0. Oh, okay, okay. So if like so, it's isolated vertex, right? Here I wouldn't do anything. I don't know, plus equals 0. I agree. Do we have to output? No, we're only interested in number of such vertices, which is very good. And sync here we should be able to get all 8. Okay. I'm not sure. I mean, we potentially can have some bugs, but I guess like penalty is only 5 minutes. And I hope that penalty is only applied if we solve this problem as a result. Do we have any details? Okay. So we answering some queries wrong. I'm not sure why. Actually, why? Am I stupid or something? This is a tree. Oh, there's one less edge than vertices, not vice versa. So 4, 4, 1, 8. Okay. Sorry, guys, I was not paying attention. Yeah, obviously trees have one less edge than vertices. Already wrong answer. Not great. Time change to test cases. Actually, we can like incorporate that case here. So something must be wrong with the intuition. And I don't know what. I mean, clearly connected components cannot hurt us, right? Because they are independent. I believe I processed like this kind of queries correctly. But whatever, well, let's try like this. It's the simplest input that I can think of. We should get 2 as a result because this connected component is not a tree. It has a cycle. You can select 1 in 1 and 2 in the second card. Yeah, I think we need to take a break to drink some tea and keep thinking about this problem. Of course, I was very stupid. Like, we duplicate every edge, so edge count has to be divided by 2. Oh my, oh my. Did we not have like any graph in which, any test case in which it is a tree? No, let me just, 2 edges from 1 to 2, from 2 to 3, right? Like previously we had, the answer should be 2 and the answer is 3. We comment and now the answer is 2. Yeah, unfortunately, I made one more wrong submission because I fixed one thing and I saw that it will fix the solution, but it didn't. But of course, yes, we duplicate every edge here, so edge count has to be divided by 2. Yeah, in case you, yeah, okay, very stupid of me. Whatever. In case you are wondering what change did I made, I changed the graph to an ordered map because I like, what if actually IDs are wrong? I didn't want to think about it. An ordered map is a bit slower, as you can see, but yeah, but it doesn't really matter. It also takes a bit more memory, but it's still okay. Okay, now I can eat a bit. I believe we're still very bad in the standings. But let's check them because I currently have no reasonable ideas for problem D. Yes, too many wrong expressions here. Also, a lot of people performing very nicely. Some of my friends actually. Okay. I guess we should go back to problem D because apparently a lot of people solved it. What's that? Yeah, like 156 people. Plus, we'll learn something about graph orientation. I mean, we already learned a bit in problem B. Let's continue. But I'll pause the recording once again because I really want to eat and I don't have good ideas at the moment. So I'll think while I'm eating. Okay. I think I noticed several things about this problem. For example, if like label at vertex u is greater than label at vertex v, then the edge uv has to be directed from u to v. That's first thing. And then I think like if vertices have the same label and we are guaranteed that solution exists, then it's because these vertices are in the same cycle. And I believe that we can detect this cycle by depth first search over only these edges that we have not decided yet. We have some cycle, right? Potential we have some edges in between, like so, or like so. You would like to find this cycle, right? Let's see what actually happens. I think we can be unfortunate if we go like the wrong way. Here, 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 here. Is it possible not to find the cycle if you're going like in DFS order? I don't know, let's see. The only way DFS can not find the cycle if you have two edges that go the same way, potentially like so. Well, okay. I think we can deal with cycle detection a bit later. To begin with, I would like to actually orient the correct edges. So vertex count, edge count. Then we will have edges. We again need utility, by the way. Actually, this is not great. Okay. Yeah, let's simplify China. We have our graph like so. And I add an edges like explicitly because I want their ID. But now that I think about it, we probably need source and this. Here we'll keep first and second. But it will mean different. Yeah, sorry for that. I think I turned my mic off so you didn't hear anything. Okay. It's getting a bit messy. I don't like how it goes. Also, vertex IDs, I believe we should decrement. Here we have vector of labels. Size vertex count. Yeah, we will think about it later. Okay. We can do it like so. Okay. Now we can also create answer at the very end. Answers. We'll loop through them. If answer, let's say if answer, then it means that H has to be oriented in the initial order that it was given to us, otherwise in such order. Okay, then we can loop through edges again and check if label at, yeah, we'll need, you know what, because it was just too long. So we grabbed ourselves a reference to the edge that we are about to change. It's perfectly fine. We'll update in the answers. If label of edge source, actually I believe it's called labels, is greater than edge destination, then we only can have like, well, let me make it so -1 will denote undefined answer. 1 will denote like this and 0 will denote like this. So if so, then so. If, however, we have opposite situations, then we have to reverse the edge. Else we have equal labels, and we would like to add them to our graph. I think so. We take edge first. Sorry, wrong snippet. Take edge second. In place back. I'm not sure whether or not we need a constructor for this, but let's. I believe we need, fortunately. We also can specify default values here. It should be a destination. It gets initialized from ID. I believe that's it. Then we can place back what? Edge. Don't necessarily need to know this vertex, right? Or actually, we could have got away with vector of pairs for graph. And we want second, and we want edge ID. Or can we? And we would also, okay, we can restore the orientation based on edge ID if necessary. We add two edges to graph, and we would like to make a series of DFS over graph and orient edges as we visit them. Okay. What is the size vertex count? All false. Vertex equals 0. Vertex most vertex count. Visited at vertex. DFS from graph visited edges. I believe we'll need them, and we'll also need answer. I believe answers. Okay. DFS won't return anything. DFS will take graph by reference. I think we actually can pass constant reference. So visited by reference because we need to update it. It would be better to pass it by pointer because we are going to change it, but our list of edges is constant. Let's change that. Answers. Answers will change, and vertex is an integer. First of all, visited at vertex equals true. Loop through. Actually, want to copy even if it's a pair. We loop through all outgoing edges, and we now, if not visited, actually no. Like we would like to orient this anyway, right? We would like to orient this thing anyway. If answers at edge ID equals -1, if edge is not oriented, it will mean that we make some more DFS calls than necessary, but whatever. If edges at edge ID for source, right? equals vertex, and answer should get 1 because it's like correct way. Else answer should get 0. And we can actually, if not visited at adjacent, we can recursively call adjacent from here. Recursively call DFS, of course. I'm not sure that we are restoring cycles correctly, but it's reasonable. I believe that DFS, like, when can DFS stop? When we have no outgoing edges from the current vertex. But we have a cycle in the graph. It means that we came into this vertex from somewhere, and then during, yeah, there was outgoing edge from this vertex. So we visited cycles that contain this vertex, right? When we run a new DFS, if there is some cycles that we has not visited, then DFS will detect that cycle, and we will have two connected cycles, which is essentially one connected cycle, right? Sounds reasonable to me. Let's check if it is. So here we should get, okay. First, where exactly? 63. Yes, correct. Destination. Source. They should be all okay, not great. Why actually? It's interesting why. Well, here we actually, I don't think that we want to change it, so we can grab ourselves an edge like so. But here we would like to change it. Okay. Suppose that we do nothing, right? Answers not found. Now answers is found. Assertion failed. Okay. If I don't have this assertion that everything works, but it does not do anything. Okay. Suppose that we only create a graph. Will it fall? Okay, so something is wrong here, around here. Very interesting, I must say. So edges are, we read edges correctly. Apparently we should read vertices correctly. Oh, of course, vertex count, what I was thinking. Okay, now it does not fail. And what if we do DFS? Well, okay. So DFS found the cycle, but this cycle was trivial. Okay, here DFS found, no, here, okay. I'm not sure whether our cycle detection DFS is correct, but let's try. Okay, very good, very good. Oh, where are we in the standings? I believe we are very low because we were very slow. Hello, excuse me. 225, not bad. I think so. I mean, how many? Okay, so we have, but these are not real participants. Show me like somebody who actually submitted something. Or do they count? I'm not sure. I believe on Codeforces, you are not a participant if you do not submit anything. Right? So will this people affect the rating? I don't know. Where are submissions actually? I don't understand. Okay, so some people made submissions. I don't know how many exactly. Oh, wait, actually, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 18, 20. Okay, so we have 131 full pages of people, which is 2,620 people. Okay. And overall registered, there were, okay, so there were 6,500 people registered. If every one of them will get some rating change, I don't think it's fair. I mean, look at these people. They all registered, but I think they are out of rating, right? Unofficial participation. For example, yeah, their rating is bigger than cap of regular contest. I think I should definitely investigate what is. Oh, actually, 1,000 records per page was a bad idea. Now I understand. Yeah, 100 per page is okay. Okay, so probably problem E was solvable. A lot of people did not get D, but got E. What is it? Given 4 integers, find the number of positive integers I. Satisfies for none of the integers between A plus BI plus B times I and A plus C times I is a multiple of D. I actually think that it's not difficult, but we won't make it on time, which is a shame. I mean, this is like an interval of length. The length of this interval is slowly increasing. At some point, it will reach D, and then there will always be a multiple of D, right? Before that, each multiple of D prevents exactly one interval from being good, right? Or no. These intervals need not be adjacent. I believe there is some sort of smart solution to this. I'll count as finance, of course we can, we already proved it. Yeah, okay, we're definitely not making it on time, but it sounds like an interesting problem. Also, let's check what is this icon. Highlighter. Okay. I believe I've seen rings on code forces. Should be the same rings. Yeah, okay, whatever. Oh, interesting. And obviously, he'll solve all of these problems now. Okay. Very, very interesting picture. Petrol must be solving problem F at the moment. Yeah, we have our friend Vlad. Vlad, it's actually pronounced. I think he's a grandmaster already on code forces. Is this FFT from Estonia? Yes. I don't see many. Okay, Bodan Pastashak, another familiar face. I believe he is an international master in code forces at the moment. Anand Daza. Okay, so Anand solved the same set of problems as we did, but a bit faster and with less rank submissions. Interesting. Actually, we solved the first problem faster than him. But then we get stuck here and okay, yes. But he also selected this order, which is interesting because I think like this was not ever very difficult, but whatever. Barachek, okay. Another familiar face, Ihor Boringblood. I don't, it should not be acceptable. I mean, what is that? Whatever. Anything else? Okay, another familiar face. But not all that many, okay. So we solved a reasonable subset of problems. Anton group, okay. So Anton solved problems a bit faster than we did, but he gathered one more 5-minute penalty. And I think with his time, he may very well be able to solve this problem as well. Also, he was not stupid about the second one. Okay. I mean, he should solve these problems and he will be okay. Because, I mean, he's top 100 here and he's also an international grandmaster in code forces. I believe we should like correct approach was would be to solve the problems now, but I'm a bit tired. I don't know. It's like what? It's first contest this week, and I have at least 2 more on these weekends. So yeah, I think this will be it for today. Yeah, let's quickly go through the problems that we solved today. Problem A was about fast modular exponentiation, which is of course binary. I guess I mean, at some point we'll have a video about modular arithmetics, and we'll cover it there. Then it was just simple math, simpler than problem like E. Problem B was to find connected components. If component is a tree, well, obviously different connected components are like independent of each other. If a component is a tree, and you can check it by edge count, by correct edge count, then you can select any subset except one vertex. If there is any cycle, then we orient the edges in this cycle, and then everything else directs to this cycle. So we kind of have a graph. We root it, but not in one vertex, but in the cycle. problem C was about processing people in correct order, in the sorted order of their weight. And we also proved that it's optimal because, like, again, every permutation is a product of several cycles. We resolve each cycle optimally. And problem D was like if one label is greater than another in the edge, then obviously this edge can only have one direction, because if we have like edge from U to V, then label at U is at least label at V, because every vertex we can visit from V, we can also visit from U by adding this edge. So if labels are different, then we immediately know the answer. If labels are the same, then we can find the cycle with the help of DFS, of series of DFS. So hope you enjoyed this kind of Livesolve plus editorial. Hope it helps. And I believe tomorrow we'll have beginner contest. We'll also we'll also participate in it. This video will come out shortly, so stay tuned. And I'll see you in the next one. Bye-bye.